Okay, so this will be the fourth lecture over chapter 6. So in this lecture, we look at this concept of standard heats of formation and use that to calculate enthalpy values for a reaction. Okay, so this is the symbol given for the standard heat of formation. Right, the superscript, that means standard state. So that means at 25 degrees Celsius, 1 atmosphere pressure. If it's a solution, then 1 molarity. And the subscript F means the heat of formation of the compound from its elements in their standard state. So that would be the most stable state of the element. So for an example, if we look at the heat of formation of water, liquid water, so if you form water from its elements, then you would be forming it from hydrogen and oxygen. So what's the most stable state of hydrogen would be H2 gas, and the most stable state of oxygen would be O2 gas. So 1 mole of H2 and a half a mole of O2 would make 1 mole of water. So if you studied that reaction on the bomb calorimeter, for example, that reaction would release 285.8 kilojoules of energy per mole of water formed. So that would be the heat of formation of water, forming it from its elements in their standard state. Okay, so there are heat of formation values known for a lot of different compounds, and these values can be found in thermodynamic tables. So this is a portion of a thermodynamic table, for example, where you see here in this first column delta H0F. So that's the heat of formation of different compounds. If you take Chem 1312 or General Chemistry 2, then you'll also study what's known as delta G, free energy, and you'll study S, which is known as entropy. In this class, we just look at the heats of formation only. So I'll say more about this table in a little bit. Okay, so what does it mean to be the most stable form of an element, that standard state? So let's take a look at some examples to illustrate. So how many forms of pure oxygen are there in nature? And the answer is 2. So when people say oxygen, they're probably talking about O2. And if you drew a Lewis dot structure of O2, you would come up with that, right? 2 oxygen atoms double bonded to each other. But you can also find pure oxygen in nature as O3. So what is O3 called? So that would be called ozone. So where do you find ozone at? You find it, it's a part of the atmosphere, the upper atmosphere, forms a protective layer over the Earth. And so if you drew a Lewis dot structure of ozone, O3, you would come up with that. So both of these are found in nature, and they're both gases at standard states. So at 25 degrees Celsius, 1 atmosphere pressure, they're both gases. So that's 2 forms of oxygen found in nature. So a new term for you is this term allotrope. So O2 and O3 are allotropes of each other. So allotrope is 2 or more forms of an element in the same state. So in this case, both gases, but one is O2, one is O3, both found in nature. So just individual atoms of oxygen, like on the periodic table, so oxygen, atomic number 8, molar mass of 15.99994 grams per mole. You do not find individual atoms of oxygen in nature, right? Oxygen atoms are just way too reactive, so they will react with something in nature if present. So, but you can find O2 and O3 in nature. Okay, so the heat of formation of any element in its most stable state at standard conditions is assigned a value of 0. So the heat of formation of O2, since that's the most stable form of oxygen, is assigned a value of 0 kilojoules per mole. And then ozone, O3, is 142.7 kilojoules per mole less stable than O2. So if we notice on this table of heats of formation values, so for example, aluminum solid, so that would be the pure elemental form of nature of aluminum found in nature, just a block of aluminum metal, and so has a heat, that would be its most stable state. So it has a heat of formation of 0, right? Anything in its most stable state is assigned a heat of formation value of 0. So you see that here with barium. If you look at calcium, right, we have calcium gas and calcium solid. Well, calcium solid is more stable than calcium in the gaseous state. So it has a heat of formation of 0, and then other forms of that element would have higher heats of formation. So one thing that you always have to be careful of when you're using this table is you make sure that you look up the substance in the correct state. So if we're looking up ethanol, for example, gas versus liquid, so you would have to know what is the problem asking about. Is it asking about the liquid state or the gaseous state? So you have to make sure you look up the right delta H value. Okay, so let's take another example. How about carbon? So how many forms of pure carbon are found in nature or are known? So for the longest time, it was thought that there were only 2 forms of carbon found in nature, graphite and diamond. So that was until 1985 when other allotropes of carbon were discovered, and that being the fullerenes. So this was a very important discovery because carbon's a pretty important element. So in 1985, new forms of pure carbon were found, and they were discovered at Rice University, which is in Houston, Texas. So that was discovered in 1985, and I'll show you what the fullerenes look like in just a minute. So just 11 years later, just to illustrate the significance of the discovery, right, the scientist who discovered the fullerenes were awarded a Nobel Prize in chemistry. So that was Richard Smalley, who was at Rice University, Richard Curl, also from Rice University, and Harry Kroto, who was from the University of Sussex. Okay, so what do these forms of carbon look like? So this is what graphite looks like. Basically, it's just all carbon atoms in 6-membered rings, but they form a sheet. And all of those 6-membered rings are attached to each other. All of the carbons are sp2 hybridized. So if you remember from chapter 10, sp2 hybridized is trigonal-planar. So all of these carbon atoms are flat. And all of these 6-membered rings are attached to each other, so they form sheets of graphite that layer on top of each other. Should be one reason that it can be used as a lubricant. Graphite can, right? And because those sheets of graphite can slide over each other. So diamond is also pure carbon. So each of these points, so this is a 6-membered ring, right? Each of those points is a carbon atom there. And then each of those carbons is attached to 1, 2, 3, 4 other carbons, right? So if we just try to illustrate, so if we, that carbon 1, so all of these carbons, right, would be attached to that carbon there. So it's attached to carbons in this direction, in that direction, and in this direction. So it forms a 3-dimensional network of 6-membered rings. And that makes diamond an extremely hard and extremely strong substance, right? It's one of the strongest, hardest materials known. So what does fullerenes look like? Well, they can look, basically they look like, well, so one form of fullerene is what's known as buckyball or Buckminster fullerene or soccer ball or C60. So it's probably the most famous version of it. So each of these points would be a carbon atom. So if you notice, there's a 6-membered ring there, and it's attached to a 5-membered ring there. So you have this pattern of 6 and 5-membered rings interconnected to each other. It kind of forms like a soccer ball pattern, but all of the carbon atoms are in a sphere. Or you can have them in a tube, so like depicted here, and you can have those rings all fused to each other to make a tube. And so those are what are called nanotubes. So which is the most stable form of carbon? Is it graphite, diamonds, or fullerenes? So drum roll please. The most stable form of carbon is graphite. So graphite then has a heat of formation of value of 0, and diamond is 1.897 kilojoules per mole less stable than graphite is, and fullerenes are significantly less stable, 2,278 kilojoules per mole less stable than graphite. So one consequence of this, so if you want to give your significant other something that will truly last forever, you should buy that person a locket of graphite. right? Not a diamond ring or diamond necklace or diamond earrings, because graphite is thermodynamically more stable than diamond. So eventually diamond can turn into graphite. So if you want something to last forever, buy a locket of graphite and you'll save yourself a lot of money. Right? But of course, if you would rather go with the diamond, which looks a lot nicer, you don't have to worry about diamond turning into graphite anytime soon. Kinetically, that's a very slow process. Okay, so let's use these delta H formation values to calculate delta H for a reaction. And so this is much simpler to do than studying a reaction experimentally in a calorimeter, and it's a much easier process than using Hess's law. So these are very simple calculations. So let's calculate delta H for this reaction. Take Fe2O3 solid plus 3 carbon monoxide gas to make 2 Fe, 2 iron solid, and 3 CO2 gas moles of CO2. Okay, so if it's not given, then what you need to do is you need to look up heat of formation values. So you need to have a thermodynamic table like this, where you can look up heats of formation like CO2 gas. It's negative 393.5 kilojoules per mole. So you would need to find all of the compounds and make sure you look up the right state. CO2 gas, not CO2 solid, for example. Okay, so if you look up the heat of formations for everything, then Fe2O3 is negative 825.5 kilojoules per mole. Carbon monoxide is negative 110.5 kilojoules per mole. Iron, so what would iron solid be? So I didn't write the value here, so see if we can predict what it will be. Well, what's the elemental form of pure iron? It would be an iron solid, right? Block of iron, so that has 0 kilojoules per mole. And CO2 gas is negative 393.5 kilojoules per mole. Okay, so it's important to note that these values are for 1 mole of the compound. So, but we have 3 moles of CO2, but this is only for 1 mole. And we have 3 moles of carbon monoxide, but this is only for 1 mole. Okay, so the key equation to use then is this. So the heat of reaction is the summation, so that means summation, right? So you're going to sum the heat of formations of the products times the how many moles there are of each one. And then you're going to sum the heat of formation of the reactants times how many mole. Right, so the N and M is representing the number of mole from the equation. And so you're going to sum those up and then simply subtract them from each other. Okay, so then if we take this reaction, so these are your products, these are your reactants. So the products come first, and then you subtract the reactants, right? So 2 goes there times 0 plus 3 times that for the carbon dioxide. And then you're going to sum those up, add those values together, and then you're going to subtract the reactants. So there's only 1 mole of Fe2O3, but there's 3 moles of carbon monoxide. So if you multiply that out, so the products, you get negative 1180.5 minus negative 1157 for the reactants. And then if you add those two together, you get negative 23.5 kilojoules. So this reaction would be exothermic by 23.5 kilojoules. Okay, let's take another example. So if we take the glucose metabolism, or really, so this would be the combustion of glucose. But this is basically the reaction that happens metabolically, right? Glucose and oxygen is converted to CO2 and water through respiration. So what is the enthalpy, what's delta H for this reaction? So the first thing you would want to do is look up heat of formation values for all of the substances if they're not given to you. So, so for glucose, heat of formation is, so forming that from carbon, graphite, hydrogen gas, and O2 gas would be exothermic by negative 1,273.3 kilojoules per mole. So O2, that's the most stable form of O2, so that has a heat of formation of 0. And CO2, and there's going to be 6 of those, so we'll have to multiply that value by 6. And 6 water molecules, so we'll have to multiply that value by 6. So then again, we take the products and multiply the 6 times the 393 and the 6 times the 285.8, add those together, and then subtract off the products, or subtract off the reactants. So if you do that, then you get negative 2,802.5 kilojoules. So this reaction would be exothermic by 2,802.5 kilojoules for every 1 mole of glucose. So of course the body then can harness that energy for the synthesis of ATP or to maintain body temperature. So how much energy is this per gram of glucose? So if we take the energy, so that's the energy per mole. And so if we get this, so this would be the inverse of the molar mass. So if we calculate the molar mass of glucose and then invert it, so then moles of glucose cancel, so then you would have kilojoules per gram. So that would be 15.6 kilojoules of energy for every 1 gram of glucose. So if we compare that to the metabolism of a fat, for example, so fats have lots of carbons, lots of hydrogens. So if we took a typical fat, C45H86O6, and with 127 divided by 2, that many moles of O2, that makes 45 moles of CO2 and 43 moles of H2O. So if we look at the, well, so here in this case, delta H is given to you. So that's negative 27,820 kilojoules per mole of the fat. So if we convert that to how many kilojoules per gram, so we need the molar mass of the fat. So this many kilojoules per mole, and if we invert the molar mass, so moles cancel, and then we have kilojoules over grams. So that would be 38.5 kilojoules of energy per gram of the fat, right? So if we take the ratio of the energies, so for the fat over the carbohydrate, so you get about 2.5 times as much energy per gram out of metabolizing a fat as you would out of metabolizing a sugar like glucose. Protein yields about 16 kilojoules per gram. So it's more efficient on a pound per energy basis for the body to store excess calories as fat rather than as carbohydrate or protein. Okay, so main concept here is simply to know how to use heats of formation values like here to calculate delta H for a reaction, and then understanding what allotropes are and what heat of formation values are. Okay, we'll stop there.